Hi everyone, thank you for being here. So today I'm going to present some results on my thesis and also where I stand within the global objectives of my PhD. So I'm doing a PhD, industrial PhD with Airbus, and the goal is to study multi-actuator spacecraft control design for line of sight pointing. So the PhD is funded by Airbus and supported by Airbus, also the AOCS department from Airbus in Friedrichshafen. And my supervisor is Andres. So first I will talk about the thesis motivation and the objectives. So more and more what happens for space observation missions is that there is more and more need in having larger quality of image and being able to see in the highest distance in space. So to achieve that, you need to maximize also the operational availability of the mission in order to be able to really observe most of the time while your spacecraft is up there, and to maximize the effective area and the resolution of your focusing device, which is usually called mirror, because a focusing device for space observation spacecraft are made of a lot of mirror. So it's like a huge lens in the end, but it's called mirror. So that's why we refer to it with mirror. And in order to improve the scientific output. So now there are new concepts emerging, which are multi-body and multi-actuator spacecraft. So what was done in the past, for example, for Hubble or for XMM Newton, which are space telescope, you had one mirror for different instruments that were not moving. So the instruments were sharing the light that was focused from the main mirror. This is for Hubble. For XMM, we have 3 mirrors and 3 scientific instruments. So the mirrors are not so big, and in the end you observe what you can with your mirror. Now the new generation of space observation mission consists in having a mirror that moves in order to focus the light to different instruments. So this is the case for James Webb Space Telescope, the future Athena Space Telescope on the right, which is the one I really based my research on. Ariel, so it's not such a big mirror, but it's the same principle, because Ariel needs to achieve high pointing requirements. So it has a primary and a secondary mirror, smaller than Athena or James Webb, but still we are facing the same multi-body and multi-actuator effects. So these are the new concepts, and as you can imagine, when you have such a huge spacecraft design, huge because also you need some room to have your focusing device and focusing focal distance inside the spacecraft. When you have such huge spacecraft, you have a lot of flexible modes induced at flexible frequency, low frequencies. So this can happen, for example, for Athena. For JUICE, it happens because of the size of the solar rays and also of the magnetic boom, which is really long. I don't know if you can see it, but it's in the middle picture. There is a magnetic boom like this, and they are also facing a lot of flexible modes with this one. So the goal or the objective is to satisfy fine pointing requirements with this kind of spacecraft architecture, and to improve also the maneuver autonomy. So if you are autonomous when doing maneuvers, you don't need always to communicate with your spacecraft in order to make it maneuver. So this will make you win mission time. And in this case of multi-body spacecraft, as I was saying, it involves moving the mirror and moving the spacecraft for the next target. So this has to be autonomous, because it's in Lagrange point, L2, this kind of missions, observation mission, because it's far away from the sun, but still able to orbit around the virtual gravity point. So communicating with the spacecraft would require 40 minutes both ways, so that's why it needs to be autonomous. And under mission constraints, because this kind of spacecraft, if the light enters the instrument, the scientific instrument, it can lead to a loss of the mission because of critical thermal, like the instruments are really, really sensitive to the temperature. So you have shields, like here, for example, you can see that on the right part, like this. This is a heat shield here, protecting from the sunlight, and the mirror is here under for Athena. So usually when you have this kind of spacecraft, you have mission constraints and attitude constraints. So the goal of my PhD is really to manage to robustly control and guide the spacecraft in this framework. So to do this, we have broken it down into several objectives. The modeling part, which is modeling the multibody dynamics of this kind of spacecraft, and then to be able to control, and a model that is also able to be robust to uncertainties, and in the framework of robust control and robust analysis, such as mu analysis tools and LFT modeling for modeling and enable to derive a control design afterwards. And then, of course, we have the guidance aspect to guide this spacecraft, as I was saying before, under attitude constraints. And then verify it on high-fidelity simulator, because these are missions in development, so the test and verification are usually done on high-fidelity simulators and not on real benchmarks and test bench, I wanted to say. So yes, verify on Airbus simulators and generalize these methods to most of the cases for multi-body and multi-actuator systems. So I developed a study case based on this, which is made of, which is a spacecraft which has a fixed main body, which is the orange part that you can see, the mirror here in blue, which is actuated by a hexapod mechanism in green. And the spacecraft has reaction wheels, more than usually, because usually with 3 reaction wheels it's enough to achieve 3-axis control, attitude control. But for this kind of spacecraft, you at least have 1 backup. So depending on this, you have different reaction wheel configurations. It can go up to 5 or 6 reaction wheels in the case of James Webb, for example, to be really agile in space. And then we also consider solar rays and solar ray drive mechanisms. So this is what I presented last year. I studied last year the modeling with flexible solar rays, and I analyzed the control with this solar ray. So this is a system I'm studying, and the attitude, and yeah, so basically that's it. And so the current status now is this year I have mainly handled the guidance part, and also a bit of modeling I haven't included here, but I have continued or finished the modeling, and I really focused on this interconnected, not interconnected, but the repointing maneuver, so interconnected, but also the maneuver under attitude constraints. And the verification is ongoing on Airbus part. So some results. I defined the guidance problem based on what I said, which is corresponding to the guidance problems for all the missions I have cited before. So which means no constraints about to rotate around the x-axis. So you can rotate 360 degrees around that axis, but then you have a sun exclusion zone. So for this spacecraft, we are located where the sun is. So, which means we cannot move the spacecraft more than 35 degrees towards us, so that so that sunlight doesn't enter the mirror. But it can rotate without restrictions in the plane of the screen here. And so that's mainly the guidance problem we are having. And usually what is done, or usually. What has been developed as an autonomous solution is based on, so it's a state-of practice I'm basing my research on, is usually that you perform, starting from an attitude, going to another attitude, you perform single-axis maneuvers to be sure that you avoid the sun. So you will first do a maneuver to cancel your elevation angle, elevation being the angle between the plane here and the sun. And so you cancel this angle, then you perform your rotation about the x-axis, and then you go in the elevation you want to for the target. So that's how this is a robust solution that can be run autonomously because it's safe. But as you can see, it leads to 3 sub-maneuvers, the first one in blue, the second one in yellow, and the third one in blue, which is Y, X, Y maneuver. So for this torque profile, and under you have the corresponding attitude angles profile, this for sure satisfies our constraint, but it's really time consuming. So I developed, based on this guidance problem, it's this guidance problem, actually the restricted zone for the attitude is a convex space. So based on this, I could prove that starting from this space and going to this space, you can find a path within this space in terms of angles. So then, based on this, I developed the torque profile in case of reaction wheel saturation. So we also take into account reaction wheel, angular momentum, and torque saturation. And based on this, I developed this coupled axis guidance maneuver. So it's coupled in terms of angles in the... sorry. It's in there? This one? No, this one. Thank you. This, it means that we don't rotate about the z-axis, we rotate about coupled axis, but the torque profile, of course, can be around the 3 axes. So we actually give a command in all axes that induces maneuver around 2 axes, coupled only. So we don't rotate about the z-axis. So this, based on this maneuver, I have done a map where I simulate all the space of constraints for both scenarios, so for both approaches. And here I represent the ratio between both maneuver times. The maneuver times from the state-of-the-art approach and the maneuver time on the coupled axis approach. So for this, for example, each pixel corresponds to the final angle, and we always start from here. So for example, if I want to perform 100 degrees in azimuth, so around x, and 30 degrees in elevation, this is the point we should look at to know the maneuver time. I have normalized the times because it's dependent on a lot of parameters. For example, mainly the reaction wheel characteristics. So based on, it's easy to, easy. We can get the maneuver time from this normalized time. And so on this picture, we can see that the ratio is always inferior to 1, which means that the coupled axis maneuver is always faster than the other one, the axis by axis. It's only for this point that it's the same time exactly, and it's understandable because then the axis by axis maneuver doesn't need to generate 3 sub-maneuvers because it's directly in the correct plane. So that's exactly the same time. But for the rest, you can see that we win time mostly for this range of elevation angles, which also makes sense because when we start from a point here and go in a point here, even with the other maneuver, we would require these 3 sub-maneuvers. So it takes time. And only moving once, accelerating and decelerating once, leads to faster times. The mean value of this graph is 0.55, so which means that in average, we're almost 2 times faster, but 1.8 times faster than the previous one. And for the regions in blue to green, it corresponds to more than 2 times faster than the previous one. So Airbus has already implemented it in a mission simulator, which is a simulator for observation spacecraft. So it has a sequence given by ESA. It has a sequence of all the targets to be performed during the mission. And this simulator also takes into account not only the maneuver times, but also reaction wheel offloading, maintenance, maneuvers, calibration maneuvers, everything. And with my guidance, they could prove that they reduced already by 20% the operational time, and they have won 2 points in availability, going from 89 to 91% of availability for their mission. So if you have, for example, a requirement of 90% of availability, then it could be an enabler, this guidance. So this, okay. And so just, this is currently what I'm doing. I'm currently on another topic focusing on the hexapod model. We're trying to see if we include flexibility in the joints and in the legs of the hexapod. We're trying to see the natural frequencies of the hexapod and to be able to simulate it. So I can say more about it later if you want. Work to be done is mainly control design. And these are the achievements during the PhD. So yeah, that's it. Thank you.